All right, if you can't hear me, then let me know, because I've been lecturing for quite a long time now, so hopefully my voice is loud enough. My colleagues certainly say it is. Anyway, okay, so Corrosion at Manchester, 65 years of excellence and impact. The 65 years, of course, comes from when the corrosion labs were established initially in the Tech, about 1957-58. So that makes about 65 years. 60 years of the MSc programme. I don't know whether that was established in 61 or 62, but the records I have were about 62. So that's 60 years. And of course, 50 years, 1972, is when the Corrosion Protection Centre was established formally, and indeed when PAXIS came about. So we're not too far away. So we're a year later. We hope to have this last year, but this things come and go, and this is where it is. So if you add all those lot up, you get 175 years of excellence. So that's how I like to see it. 175 years of excellence in corrosion. So what are we about? We're about this. I like this movie. This is one of the things we show students in teaching. If you look carefully, you can see about here a square crystal somewhere. Here is about there. There somewhere. There it is. That's crystal salt. So this is sitting next to the sea. It's been time-lapsed photographed, and you can see these patterns of rust forming over the surface. You can also see areas which are completely unrusted and areas which are rusted. These are obviously anodes, and this is a cathode. So those of you who don't know anything about corrosion, you've got to get a teach-in at the moment. So let's do that again, because I quite like this. You can see this is just unpainted steel. It's not got any oil on it or anything. Off it goes again. And these are filiforms going across the surface. And it's a well-known mechanism for this. You can see iron chloride forming, the dark stuff, which then oxidizes in air to form the dry iron oxide. This is just atmospheric corrosion occurring, actually on the building site, next to the ocean, next to the sea, over a period of a few weeks or months. But rusting is, of course, only a small part of what we're about. Here's some samples from our corrosion museum, which I've managed to save and bring to this building. And so we're about intergranular corrosion, stress corrosion, cracking, pitting, general corrosion, inhibition, CP, dealloying, I won't read them all. But there's a masses and masses of physical, chemomechanical problems associated with corrosion, and that's what we have to do. Physical, chemomechanical means that we need to understand all of those things, physics, chemistry, mechanics, to understand corrosion, which is why it is a complicated subject and why very few people do it properly and do it well, and why there's only a very few limited number of organisations in the world which educate people at this level, and we're still the best. We're not the biggest because Robin, many, many years ago, went to China to help them set up their corrosion protection centre, which now educates vast numbers of Chinese in this area, so I blame him. So, you've heard about this, but I've discovered that the first PhD was awarded in 1960, the electrochemical behaviour of sprayed metals, based on aluminum, by Webster. T.K. Ross, supervisor at the Department of Chemical Engineering. Now, a little bit of rummaging around the library tells me that 51 PhD degrees were awarded from about 4 to 6 academic staff in the time of the corrosion laboratory strictly. And after the Corrosion Protection Centre was set up, a further 515 PhD degrees have been awarded. That's more than 560 PhD graduates in that time. So we're graduating more than one PhD student per person per year, which essentially means, since a PhD takes a minimum of 3 years, we all have at least 3 PhD students all the time. And we've had that before it became a university requirement. Now we have more PhD students each. PhDs take longer now, so we have more than that. So there's a vast number of graduates out there. 62 at the top there. The MSc was called Corrosion Science. Then it turned into Corrosion Science and Engineering. Then it turned into Corrosion Control Engineering, which was part of a joint master's programme, or jointly advertised master's programme with the Manchester Materials Science Centre, called the Manchester Materials Masters. And at that time, we also developed an online program. We were the first to do this, developed for campus-based and distance learning students. We still have that online program, although it's not for distance learning students anymore. That program was discontinued. 2016, we started a fourth-year undergraduate MEng option. Now, I don't have accurate figures before 1985, because 1985 was when I was hired. However, 973 MSc graduates I have taught. By the end of the cohort this year, I will have taught more than 1,000 MSc students. We're approaching 1,500 MSc graduate students over the life of the Corrosion Protection Centre. Here's some teaching. Some of you may remember these old photographs. They're still very good. There's the mill where it all happened. Somebody doing some electrochemistry there. There's somebody looking at an old-fashioned galvanic corrosion experiment, looking at the anode and cathode. Pink is the cathode, and blue is the anode. Here's people looking at a sample of a tube and shell heat exchanger, which corroded at the top. And here's someone looking at corrosion potentials in rebar. This is the sort of thing we do in the corrosion laboratory, teaching laboratory. Plenty of other examples, and this whole gamut of experiments, which is fairly standard, has been transferred now to this building. By the way, that's the tech, that's UMIS, and indeed UMIS, that's UMIS, that's where we are now, and that's Corrosion at Manchester. We also operate or developed a MOOC, a massive online open course under the Coursera platform, and so far, we have 4 or 5 modules. Some people can do a 5th module on organic proteins. We've had almost 16,000 people on that course, 3,000 completes, currently 10,500 are active. Okay, it's one of the most successful massive online open courses that the university has operated. Not the biggest, but certainly the most successful, with the highest average user rating. Most of the user ratings are because I have to buy to get a certificate of completion. But that's the platform, Coursera, nothing to do with us. We're going to extend this shortly. So what do we do? Here's a couple of videos. The first example I'm going to show you is one which you should all be familiar with. This is a piece of an alloy wheel from a car. Obviously it goes all the way around like that. Now the alloy wheel is made of aluminium alloy, and it's painted. It might not look as though it's painted, but these dark colours are from the powder coating, the paint powder coating that's put on the wheel for corrosion protection. When you bump your wheel against the curb, it damages the paint system and the wheel starts corroding. And we've shown this here by damaging the paint coating artificially and exposing it to the atmosphere, and we get this very pretty corrosion which we call filiform corrosion. It is, of course, not damaging to the mechanical properties of the wheel. The wheel is perfectly okay, but it is damaging to the aesthetics of the wheel. So this is an example of corrosion that does not cause mechanical damage, but cause aesthetic damage. So we've got about 15 of these videos showing some of the corrosion samples that we have in our corrosion museum, and we're going to do some more. We set these up for the COVID time, where people couldn't actually handle these materials. And now they can get back into class and play with them, but we're going to expand the number of videos we have. That was done professionally by the university AV team. This is another one.
This short animation is going to show you how we use one of the most important techniques to monitor corrosion in oil fields. This animation here shows you an oil field processing facility, and the pipeline in the middle is one we want to focus on and are concerned about its corrosion. Here we see a corrosion coupon which we are going to weigh. This is before we've inserted it into the pipeline, so it's nice and clean, and we're using a set of accurate scales, so we can get precise scales, so we get an accurate weight measurement. So it's being weighed, and typically we will use 2 corrosion coupons inside the pipeline at any one point, so we get more reliable corrosion rates, and you'll see that here. You can see the corrosion coupons being mounted and entered into the top of the pipeline, and you can see them there dangling into the pipeline. You can see in this close-up that they need to be isolated from the metal support on the pipeline itself, so we avoid any galvanic corrosion. And remember, the corrosion coupons should be of the same material as the pipeline. And the isolation is achieved by using PTFE washers and inserts, quite typically. Here we have a side-on view of the pipeline, and you will see that we can insert these corrosion coupons at different heights depending on the flow conditions. For instance, we might have stratified flow, where you'll see where we insert the third coupon here at the lowest point where we might want to sample the liquid. Once they've been exposed for a certain amount of time, say 6 months or 3 months, then they're corroded to a certain extent as shown here, and we need to reweigh them. However, it's important that prior to reweighing, we have to clean the corrosion product from the sample, either by physical or chemical means. We then can reweigh them, calculate the difference in the weight, find out the material lost, and then calculate the corrosion rate.
So those are some examples of some video teaching that we do. Obviously not everything is video taught like that. We have most of it is normal presentations. Sometimes we voice over the presentations for online delivery. But those are some examples of things that we would like to try and expand on.
The first example I'm going to show you is short animation.
There we go, that's better. We've heard enough of that person, I think. Okay, now in looking at research activity, it's very difficult because of the way the research funding landscape changes over the years to actually show, as we showed in teaching numbers, to show the funding. What we can do is have a snapshot. I've had 2 snapshots done recently, one in 2016 and one in 2020, which shows very similar results. There were 11 staff at the end of 2016. So I guess a 2017 snapshot really. 11 staff, about 60% of the metallurgy and corrosion research theme. So just to explain, in the school of materials, there's various research themes. One of them is called corrosion, metallurgy and corrosion. And we are about 60%, or certainly at that point in time, we're 60% of that group. At that point in time, we held more than £12 million in research grants, of split about 1/4 RCUK, EPSRC, and 3/4 from essentially industry. In terms of prestige, the EPSRC ones are more valuable, but in terms of income, the industry ones are much more valuable because they come at full economic costing, or even more than full economic costing, whereas the EPSRC ones comes at 80% of full economic costing, which means if you take that to its logical conclusion, if you get a large EPSRC grant, the university makes a loss. We produced 71 unique publications, 6 to 7 each at that time. 19 postdocs, 59 PhDs, 28 MSc students, 6 visiting scientists, between the 11 of us. Now that is something like twice the research intensity that we are required to do as an academic in the current university. Well, I thought it would be interesting to look at research outputs over the years. This is publications. So when it was the corrosion laboratory at the Tech, these are 5-year bins, by the way. When it was corrosion laboratory at the Tech, 96 papers, publications were made, unique outputs, 1.5 per academic per year, approximately. When it became the Corrosion Protection Centre, it jumped, because of course there were more people there, but also the people had a higher intensity of activity. We had 1,000 or so unique outputs over the time there for the Corrosion Protection Centre to 2004, roughly 3 per academic per year. But you can see this kick-up here. This kick-up was happening from about the 1980s onwards. When we joined University of Manchester, we're now publishing twice the rate we published when we were under the Corrosion Protection Centre. 6.8 papers per academic per year. That's a hell of a rate, really. And in a sense, we're required to do even better than that. I think that's quite a good performance. 78% journal articles, 18% conference articles, 4% other articles. So anyone who says we don't do very much, we don't publish very much, this is the evidence that that's completely wrong. We publish a lot. We have a huge impact in terms of academic impact, but we wouldn't get that impact if we didn't have the industrial funding. And the fact we do have the industrial funding shows the commercial impact we make, because they wouldn't give us the money if we weren't going to do a good job for them. Robin mentioned fellows and fellowships. Well, we have fellows and fellowships from all these people. That's the Royal Microscopical Society, MRMS, by the way. NACE International is now AMMP, but I prefer NACE because AMMP doesn't mean anything to me. I.M3 is History of Materials. Again, that doesn't really mean very much either. ECS, the Electrochemical Society. So I think there's one role. Graham Wood was a FRS, and we have had 4 other FRNGs in the group. Prestige medals and awards. So Graham won most of these, but some of us have won some of them too. So the Calvin Award was a Graham Wood. IOM3 gold medal, that was George Thompson. Graham Wood, well, the entire group actually won the European Corrosion Medal twice. It's the only group of people that have won the European Corrosion Medal. That's the European Federation of Corrosion twice. Okay, that's for a group of people working at the highest level. So, well done everyone. The Queen's Anniversary Medal was won in 2002. That's for the Corrosion Group and also Capsis at the university. The Bealby Medal was won twice, one by Graham Wood, one by George Thompson, and the Henry Clifton Sorbet Award was Grace Burke. All these are very high prestigious awards. But we've also won lots of other awards too, too numerous to mention, but one we have to mention because of the Institute of Corrosion, because 4 presidents, and a past president as well by the way, are here, are the Johan Revens Award. So we have 6 awardees, and there's Bob and Mary, another former student of ours now at Imperial College in London, fighting it out over who's got the best sword to fight corrosion. So one of the things that academics do, or used to do when I was first hired, was to write research proposals, usually to the UPSRC, and get a very small amount of money to do as much as you can with it. And you have to keep writing proposals and writing proposals and writing proposals. That gets tedious, and the success rate for writing proposals goes down and down and down. It's down about 18% now, I think it is. So as one administrator said to me, if the success rate is 18%, you just have to write 5 a year, and then you get one of them. I don't think they fully understood what writing a proposal is all about. Anyway, so what has been happening, the trend over the last 20 or so years, is to develop big research partnerships. And one of the first ones, I think the first one at UMIS certainly, was the BNFL Materials Performance Centre, which was a £2 million investment with 3 academic staff hired and a director. And that led to more than £10 million of additional funding over 5 years, and essentially led the nuclear renaissance in research in nuclear and the establishment, ultimately, of the Dalton Nuclear Institute and the rest of the materials there. Without a corrosion group, that would not have come to Manchester and may never have existed in the first place. The second one was the BP Centre in Corrosion Materials. That was a £2.5 million investment, with in fact the first Royal Academy of Engineering chair in the entire university was in corrosion materials. Bob Eckert. That appointment led to £3 million of additional income from the EP and others, and the eventual establishment of the 10-year ICAM, International Centre for Advanced Materials, which is now being extended out to 2035, I believe. EPSRC, a good example, is LATEST, which is a Light Alloys for Environmentally Sustainable Transportation, which is a collaboration between the Metallurgy Group and the Corrosion Group. And it's one of the few programme grants that has had a second programme grant on more or less the same thing as the first programme grant, which shows how important that type of material is. So 2 5-year EPSRC programmes with large numbers of people supporting partners in the automotive and aerospace supply chains. And I can go on. £2 million investment from BNFL and the Rad Waste Disposal Centre. A DIRT was appointed on the back of that one. EDF Energy, the second REng fellow in the entire university was the EDF Energy fellow, which Brian Connolly holds. Akzo Nobel, which is my particular appointment. That was a £3 million investment over 6 years, now been extended through to 11, possibly 12 years. And the Henry Royce Institute, leading contributions there in materials for demanding environments and in nuclear. And it's arguable that without corrosion group existing, none of these things would have happened, or if they had happened, they would have happened in completely different ways, and probably far less intense, with far less intensity. So, a couple of research highlights. What did we do? This isn't a half gigabyte memory stick for nothing. This is a piece of research from which I thought was quite good. Lovely movie, and I thought Robin would like this. This is hydrogen cracking of a hydrogen-charged austenitic piece of stainless steel. This bit here shows the stress and strain rising up, and you'll see the cracking occur here. It's being pulled in that direction. You can see the twins beginning to develop in the grains, and you will eventually see cracking happening around about here. You can see cracks beginning to develop there and here at the grain boundaries. This is not a sensitized alloy, by the way. This is just where the triple points come and load up. Eventually it will break. If you want to ask about this, then Dirk knows all about it. But that's a time-lapse photograph using confocal optical microscopy on a cracking piece of austenitic stainless steel, which in a sense shouldn't really hydrogen crack in the first place, but it does. And finding out why it does is really important for many industries, including oil and gas and others. Corrosion inhibitors. Rob gave me this one. This isn't a movie, but what it is an indication of what we don't know, which is what some of the things we've been doing are exploring the research ideas or the practical ideas that everyone knows is how things work. Everyone knows paint works like this. Everyone knows austenitic stainless steels don't crack. Everyone knows these things don't happen. Everyone knows inhibitors absorb onto surfaces in a particular way, except they don't, because they've never really looked at it in sufficient detail. So you assume that an inhibitor will absorb on a surface in an acid independent of the acid. But that's not in fact the case. If you look here, you'll see that in this case, the inhibitor, omit, which is this stuff here, basically it's a head chain, an amine, or an amide, and a big long fatty acid chain. In hydrochloric acid, it absorbs through an iron chloride intermediary, and in sulfuric acid, it kind of maybe does or doesn't absorb, but onto ferric sulfate surface. So it doesn't really inhibit in the way you imagine it inhibits in the first place. Because only by understanding this detail, this very, very precise detail, that we can begin to develop inhibitors which will function in a designed way rather than just we'll try it and see, no, it doesn't work. We'll try it and see, no, it doesn't work. And after 100 tries and sees, you might get one that might work. Same thing with paints. Another one from Dirk. This is a tomography picture. So what we're looking at here is the annealed duplex microstructure. Corrodes in different ways because of the duplex structure where you have ferrites and austenites with different compositions. So this is a tomography picture, X-ray tomography. Another movie, and well, quite a lovely picture. That's what the pit looks like on the outside. And we've always wondered what pits look like on the inside. Well, there we go. We can now tell. Okay, so you can use that information to understand how the pitting process works in 3 dimensions, not just 2 dimensions. And I don't have space to do the annealed. This is the annealed duplex microstructure. The quenched duplex microstructure pits corrodes in a completely different way. A single hemispherical pit, essentially. So my own work, I thought I have to shove something in from my own work. This is pigments in paint. Pigments in paint, everyone knows, paint works. You put the inhibited pigments in, they leach out, the active ingredients go to the surface. But what happens to the things that leach out? You know, if they leach out, surely there must be voids in the paint. And the usual understanding is, no, there are no voids. Or if there are any voids, they're not big enough to do anything. So let's have a look. This is a piece of wire painted at the end, a rod, and that's the X-ray density map. Because the density is dependent on the absorption, the density is dependent upon the atomic number. We can separate the components of the paint out. What's happening here is we're just segmenting the image on a grayscale to remove the things that we're not interested in. So after one day, just kind of stop it. After one day, we've taken away the organic coating components, and we're left with the green bits, which are the active inhibitors, and the yellow bits, which are the voids where the active inhibitors being dissolved. If you think about it, if it's going to dissolve, of course it's going to leave a void, a measurable void. What happens to the paint with these measurable voids? There we go, there it goes again. As you can see, that's after 1 day, after 3 days, that's 7 days and 14 days. You can see the void, the leaching process migrates further and further through until we get a pathway right away from the exterior environment to the substrate, fairly quickly actually. So paints that are actively inhibiting also create holes in them which allow the environment to get to the surface. So it's a miracle they work at all, in a way. But again, knowing this, we can now design the paint or the pigmentation to have the correct size, the correct morphology, the correct spacing. If it's too far apart, the pigments don't dissolve, because the water never gets to it. If there's too much pigment there, then we create huge, great big gaps. So there used to be an idea that the more pigment you put in, the better inhibited. That's not the case. There's a sweet spot. Now we know what it is. We can design for it. I put this bit in because I kind of put it upon myself as a sort of charitable appeal to support bursaries. My bosses always say there's not enough MSc students. Actually, if you look at 35 years of MSc students, it's 26 is the average. Completely flat. Doesn't go up, doesn't go down. 26. Sometimes you get more. So every time you get a blip of 35 come in, and the bosses say, you had 35 last year, you must hire 40 next year, otherwise you're failing. But that never works, because it will go down to maybe 16 the following year. But the average is still 26. 25 or 26. Hasn't changed. So we educate all the possible MSc students you can possibly educate who want to come here every year. There is no bigger market, because we haven't. That's the important point to make. But one thing we can try and do is encourage people, particularly final year UK and undergraduate students, to do corrosion. And with the benefit of Institute of Corrosion, they have kindly offered $25,000 a year to help bursaries. We'd also like to support people who are perhaps poorly represented or underprivileged groups to come along and do corrosion as well. And we'd like to raise money for that purpose. We'd also like to raise fellowships for the support of the next generation of academic leaders in corrosion. I'm almost retiring. Many of my colleagues have already retired. So we need people to replace them. There's no guarantee that the university will replace us. The only way we can get replacements is to raise them ourselves. I'm very pleased to say that we think we have raised sufficient money from a donor to pay for an academic research fellow, which hopefully will turn into an academic post if they're successful. But more is needed. I haven't put all the names there because I can't remember, I don't know all the names. But I have put as many as I can. But the most important bit is the bit at the bottom in green. That's why I started the job in the first place, and that's why I continue. It's the graduates who graduate from here and come back to us. I remember as director of research in the school, materials, asking people what makes you come into work every day. And answers I got were the amount of money I raise, how many papers I publish, whether I got a Nature paper recently. None of them said the students. Without the students, we're not here, we don't have a job. So in my mind, it's the students that create our role, and it's their commitment and enthusiasm that inspires us. Thank you.